Hello, everyone. Good afternoon. It's been a long week. It's been a great week, full of interesting talks and discussions and posters. But I hope everyone still has some energy left for one last piece of science. It's my great pleasure to introduce the last keynote speaker of this year's annual science conference, Tom Langbehn. Tom is a researcher at the theoretical group, ecology group at the University of Bergen, and is a self-described ocean-going modeler. Over the course of 10 years, across his master's, PhD, and postdoctorate research, Tom has studied the mechanisms that tie together life and light in the open ocean, and in particular via the prism of pelagic fish in high-latitude extreme environments. Tom's research combines modeling, field experiments, and observation, and really tries to lay weight on a factor that is overpresent in all of the marine ecosystems, but perhaps often overlooked or ignored. So, as Tom takes the stage and reveals to us the hidden influences of light and its absence on the ocean, it is perhaps fitting that we all sit in the comfortable twilight of this auditorium. Please give a warm welcome to Tom Langbehn.
Thank you so much, Côme. It's a great honor to be standing here, and I must say it's really humbling, especially after I have witnessed so many great presentations from the early career group here at ICES, to be standing here and representing the early career scientists in the room. I'm just gonna jump right into it. I think we are running a bit late, so I'm not gonna have more introduction. I think when you or the most people think about light in the ocean, then they are thinking about the effects of light on primary production, how light is driving photosynthesis, and they're generating the energy that then sustains all higher trophic level. But light has a twofold impact on life in the ocean. It also affects top-down control. And it affects top-down control through the individual foraging and interactions. And many higher trophic level predators, from invertebrates and fish to birds and even up to baleen whales, they use vision and therefore light to effectively capture their prey. In life history studies, or when assessing the vulnerability of species to climate change, however, there's often a strong focus on how organisms allocate their resources. And this how they allocate their energy and resources to, for example, growth, metabolism, or reproduction. And the focus there is very much on temperature. And Jenny has reminded us of that fish are ectotherms, and we cannot overlook the effects of temperature when we study them. I would like to expand a bit on that and say, fish are not only ectotherms, they're also visual predators, and therefore we should not overlook the effects of light and temperature combined. After all, sensing is a very first critical step here, because you cannot allocate energy that you haven't digested and spotted first. And I believe that light is an often overlooked key factor in marine ecosystems. And just to confirm this, I want to ask the question to the room. Who of you in the room has included temperature as a driver in their studies? By raising the hand. Yeah, that's the vast majority. And if I can turn the question around, how many have included light as a key driver in their study? Surprisingly many hands as well. That's wonderful. I feel there's a certain bias here because the acoustics has been one key session, and I think we don't get around thinking about lots of these organisms without light. But I want to start broad. Light is extremely variable in the ocean. Marine lightscapes typically cover around 9 orders of magnitude in terms of their surface light. So there's 1 billion times more light reaching the ocean surface on a sunny day during midday than during a starlit night here. And there is still about 1 million times more light under a full moon. And when we are moving down in the water column, then light declines exponentially. Note that this is drawn on a log scale here. And this means that only about 10% of the surface light in clear water will penetrate down to around 100 meters, and only 1% will reach 200 meters in clear water. And this is what we often use to outline what we call the epipelagic or euphotic zone. Overcast, so cloud cover, will further reduce the light intensity at the surface and therefore also affect the lightscapes below. And this means that the light intensity during a moonlit night here is roughly the same at the surface than it is during a cloudy day at 500 meter steps here. And just to give you another point of reference here is that copperpods are so light sensitive that they can detect the faintest starlight down to around over 100 meter steps during a clear day. Many other organisms would even be able to detect light at much lower light intensities. When we're moving closer to the coast in the murky coastal waters, so where the turbidity and the light attenuation is greater, we see that the euphotic zone becomes much shallower. So just as a reference here again, only 1% in this case would typically penetrate down to around 80 meters instead of the 200 meters in clearer waters. And it is this lightscape that is the backdrop to a lot of the predator-prey interactions that we're witnessing in the oceans. So the detection distance of predators greatly diminishes as light decreases, both at night but also with increasing depth. And this is important because already small changes in light can have a disproportionately large effect on the search efficiency of certain predators because the visual detection distance scales non-linearly to the search area, which is a proxy for the search efficiency here. We also see that in coastal waters, the vertical foraging habitat becomes much narrower because of light attenuation. And lastly, larger organisms are generally detected further away than smaller organisms, and therefore they have to go deeper to reduce their visibility. And some of these ecological dynamics are beautifully illustrated in this study from a couple of years ago by Oman and Romagnan. So what they are showing is that the larger individuals typically stay deeper here, as illustrated in the uppermost panel here. They show a clear diel vertical migration patterns here with the white dots, the daytime distributions typically deeper than the nighttime distributions. And they also show that the intermediate size classes are the ones that have generally the largest amplitude in this diel vertical migrations. And they reason that the small organisms here at the left-hand side of the scale, they're typically too small to be preyed on efficiently by predators, whereas the larger ones, they are so big that they're even detected in faint light conditions and therefore stay deep even during nighttime. The study also illustrates the effects on turbidity on vertical migrations. So what they are showing is that as we are moving into more turbid waters, that the migration amplitude becomes smaller. And generally, we see that the distribution also becomes shallower as we are moving from the open ocean to the near coastal waters here. But it is not always possible for organisms to go deep and hide in the darkness. My colleague, Johanna Orflot, another early career scientist in the room here, she has looked at a lot of zooplankton samples from the Barents Sea, and she confirmed this trend. So what she clearly shows is that smaller copperpods generally tend to stay shallower than the larger individuals. But what her data also shows is as we're moving up into shallower waters, some of these larger organisms get caught in light intensities that are several orders of magnitude larger than their typical daytime habitat. And this has, of course, consequences if we think about visual predation. And it is the reason that we don't see any large copperpods on the shallow banks in the Barents Sea. This is not because the environmental conditions there are not favorable, it is just because fish are feeding on these copperpods faster than we can sample them. And This distribution explains well why we don't see any copepods on the banks, and it explains why we see them typically distributed here in the more deeper areas to the south, where we have bottom depth conditions that are usually below 360 meters. But it does not really explain why some of the copepods are also found in much shallower waters up here to the north, at depths that are not so much deeper than the shallow banks. At this point, I want to share the stage with another key collaborator on this project, Jennifer Freer. She is an ecosystem modeler at the British Antarctic Survey, and she has been very instrumental also to get this analysis going. So if we're trying to tease apart a bit the distributions in the Barents Sea, then we can see that the southern part of the Barents Sea is very much dominated by Atlantic water masses that are pushing onto the shallow shelf here through these deeper troughs. And in this area, most of the copepods are actually belonging to one genus, the genus Paraoiketa here. This is a deep water species that is widely distributed across the entire North Atlantic and tends to stay at twilight zone depth, so between 200 and 1,000 meters usually. But what we are seeing is that they are washed into the Barents Sea through the troughs and then pushed onto the shelf and eventually onto the banks where they become food for the planktivorous fish. Very similar we see in the north, one genus that dominates the abundances there. This is Calanus hyperboreus, another large copepod species that typically is found in deep ocean basins because it has a diel vertical migration strategy, a seasonal vertical migration strategy where it overwinters and hibernates at great depth. And we are seeing that this species is also pushed through these channels into the northern Barents Sea, and that the distribution very much overlaps with the seasonal sea ice extent here during summer. So how do we explain that they thrive in these northern conditions here where it is shallow? Sea ice, especially when snow-covered, is very effective in blocking light from reaching the waters below. So the light intensities here on these northern banks at around 180 meters depth, they are very much similar to the light conditions at more than 300 meters depth further to the south in ice-free waters. And because the light conditions are similar, we would also assume that the predation rates on this species is similar in these similar conditions here. However, that sea ice refuge in the north is dwindling. We are seeing as a consequence of global warming that the Arctic Ocean will become likely a much riskier place for these large copepods. And our models predict that in the northern Barents Sea, planktivorous fish may become up to 16 times more efficient in finding their prey, and this may very well have ripple effects along the entire food web. In other areas, in Greenland, for example, we are seeing already a shift towards smaller and less fat-rich copepod species in areas where the sea ice is retreating. The Arctic Ocean is unlike any other ocean in the world. It is the only ocean at high latitudes. So if you compare the southern and the northern hemisphere, then you will see that about 2/3 of the area above the Arctic Circle in the north are actually ocean, whereas around 2/3 in the southern hemisphere would be covered by land. And in this case, it's the Nordic seas that are, again, standing out because it's the only ocean area that remains ice-free year-round. So you can watch the animation and follow your study area, and you will see they all become sea ice covered. The only area that stays ice-free is this area. And I would argue this is the area where we should maybe look for answers on how the Arctic Ocean is going to look in the future, because it is already influenced also by the intense seasonal light environment that we are seeing in the Arctic. So what could possibly effects be once the ice is gone? Although sea ice loss will change the underwater lightscape, the seasonality of light, of course, is unaffected. The photo period itself will not change with warming temperatures. While the midnight sun may allow fish to forage at a rate of 24/7, the darkness of the polar night, however, will constrain and limit their visual foraging activities also in the future. So this creates a light environment that very much favors seasonal migrants, which have the capacity for this long-distance migrations in and out of the Arctic, and we will likely see that some of them are exploiting the summer situations here. Likely candidates in our waters will be probably herring or mackerel, I would say. But not all species may have the necessary adaptations to thrive at high latitudes. The current thinking is that as species track their optimal thermal habitats across latitudes, however, this considers only temperature and often ignores that also species moving north will encounter increasingly seasonal light environments. Meaning that towards the pole, even if species A only shifts, or if species A shifts a considerable distance here, it will only experience a very minor change in the light environment. Whereas species B and C at higher latitudes, they will experience very much drastic changes in their light environment. And in the case of species B, for example, the shift from a circadian, so a day-night cycle, into a seasonal light environment. And I think it's not surprising that this requires very much different strategies and adaptations to survive and thrive in such an environment. We have tried to model some of these consequences for two different species groups, and I will give two examples here. One where the polar night is the limitation, and one where the midnight sun period will act as a barrier to the northwards distribution shifts. I'm going to start with herring. And I want to give a quick shout out to my colleague, Gabriella Lyngström. She is the one who has developed the model and really driven the thinking for this part of the story. Starting with herring, herring fattens in autumn to survive the long and dark winter with little production and light to search for food. And this particular herring stock here in Norwegian waters has a spring spawning life history, meaning that the energy left in spring is used to produce offspring. However, as temperatures are warming, we will see an increase in all biological rates, meaning also that they're going to burn faster through their energy stores, which will leave them with less energy in spring for their spring spawning life history, which has, of course, direct fitness consequences. And this loss they cannot compensate for in situ or by shifting northwards, because as they would shift north, it is not only that the temperatures are staying stable, but they will enter again a more seasonal light environment here. So the polar night becomes longer as they are shifting further to the north. So consequently, winter darkness is a barrier here. But as I said before, with the continued sea ice loss, we will likely see that some of these species may exploit the summer season and migrate into these high latitude waters. A very similar argument can be made for mesopelagic fish. These are cosmopolitan species usually that we find in all major ocean areas, except for the Arctic. And they are usually diel vertical migrators, so they prefer to stay in this twilight zone habitat outlined here in gray. And at low latitudes, they will use or track this this light habitat and perform diel vertical migration. So a mesopelagic fish that follows this light comfort zone has no perception of light and dark. It always stays in the twilight, so it always stays in the same light intensities, which also means that it's always equally safe. So meaning at night, predators will not have the light conditions that are right for them to spot this mesopelagic species. They are usually safe when they're getting closer to the surface waters, and it is there that they overlap with the prey organisms. At high latitudes, however, it is never safe near the surface because the midnight sun will never allow the twilight zone to shift towards the surface and overlap with the prey distribution. Which means that they are faced with two poor options. So either they stay down at depths where prey is scarce and they will eventually starve, or they take the risk and do this foraging bouts up to the surface, where they then are very likely to become prey to some of the other piscivorous predators in the area. And this is why in our model we predict that the areas north of the Arctic Circle are sinks for mesopelagic species. And in this case, it's the midnight sun that is the barrier. And also here, warming is not going to change this. A very similar explanation, because with increasing rates, mesopelagic fish would be hungrier and they would be forced to take that risk to migrate to the surface layer more often, and thus increase also their risk of predation. But then we can ask, how well are these model predictions grounded in reality? And mesopelagic fish abundance has repeatedly shown to decline as we are moving towards higher latitudes. And one striking example comes from the Davis Strait, which is up here on the west side of Greenland. And what this echogram is showing is that the acoustic backscatter, as an indicator of biomass, is rapidly dropping across the Arctic Circle. And sampling has revealed that the communities on both sides here are very different. So to the south, we have communities of lots of diel vertical migrators, some of the myctophids of the mesopelagic species that I have already mentioned, whereas in the north, the communities are dominated by boreal species such as cod and some of the snail fishes. The authors of these studies have pointed towards temperature as one of their main drivers. And they're obviously right, because these are two different water masses that we are witnessing here. I would, however, argue that we should also consider the origin of these water masses, because it's the origin of these water masses that are the conditions from which some of these advected expatriates originate. And then we have the polar waters flowing south that originate in seasonal light environments, in which we have predicted to be sinks for certain species. And then we have the warmer Atlantic water masses flowing north, and they originate at latitudes with a clear day-night cycle, where we have predicted some of the source areas for this species. I think this is a very good example that illustrates how difficult it is to disentangle the effects of temperature and light sometimes. Another area where I think the lines between light and temperature are blurred is the North Atlantic. So we are seeing very much the warm water flowing north on the east side, on the east side of the basin, and colder polar water masses south on the western side here. But in accordance with the model, we find that north of Svalbard, at least, we have some scattering layers. They are non-migrating, and they're usually found at depths between 400 and 500 meters. And we also know that there, similar to what we have seen in the Davis Strait, we are witnessing a change in the community, and lanternfish there only contribute about 2% of the biomass. And I would argue that these mesopelagic fish are not the strongest swimmers. Even though they do this diel vertical migrations, they're often only finger long. And sustained swimming against current speeds that are sometimes about 3 times their body lengths, I think would bioenergetically not be feasible. So they are probably advected similar to zooplankton and are drifting towards these high latitudes. And then considering that about 7 Sverdrups, or 7 million cubic liters of waters, are flushing across this Iceland, Faroe, Shetland ridge per second, we could ask the question, to what degree do some of these advected species sustain high latitude food chains? And I want to step back for a second here and consider what we have looked at so far. So what we have seen is that foraging hotspots emerge where prey is either flushed onto sunlit banks, or where prey is flushed from the dark beneath sea ice into sunlit open oceans, or carried north by currents into seasonal light environments. So I would say that more generally, we can say that rich feeding grounds are found where prey that typically hides in the darkness becomes exposed to light and makes them easy target to visual predation. So the key takeaway here is that advection turns ocean currents into food conveyor belts that ecologically link systems distant in both space and time. And if we go back to the example of the Barents Sea and the copperpods being washed onto the shelf, this is production, primary production that originates, for example, from the Norwegian and Greenland Sea and sustains secondary production, so the fish stocks that we are harvesting in the Barents Sea. And this, of course, then would also have consequences how we think around ecosystem-based management and the scope of ecosystem-based management if we consider spatial scales here. I also think that we can apply this concept more broadly to understand where flourishing ecosystems emerge. If we take the case of mesopelagic fish again and acknowledge that they are drifting with the currents largely, then I think that rich species are not only fueled by primary production locally, but rather by advection of some of these species from the areas that we typically consider ocean deserts. At least in our biology lectures, the textbook still calls the open oceans as biological deserts, but I think this ignores the fact that there is a lot of production in these areas too. But that production is typically out of reach for predators, but it becomes available when it is drifting towards the edges of these ocean basins where it meets the slopes, where organisms are again pushed up into the light, and where we then see rich predator communities that are really lining these edges, and they are forming basically a wall of mouth that is standing on this edge and strips water or prey from the currents as it flows over the crest of the slopes. One case that illustrates this very well, I think, is the case of Greater Argentine. So I've just indicated the general distribution here. This is data pulled from the ICES database. And what we know from acoustic observations is that the species is found at depths between 200 and 600 meters typically, relatively close to the bottom. But if I then in blue highlight areas that also fall into this depth range, 200 to 600 meters, you will notice that there are several areas where the species does not seem to occur. I know for some areas that is a sampling bias, so I know that German colleagues are sampling up here, and we know that they are catching a lot of Argentine, but there are certain areas where we are for sure that this is a real distribution that we are seeing. And if we zoom into these 4 key areas, I think we can highlight a few more trends here that are quite interesting, I think. One is that the species is predominantly found near the shelf break, but not on the adjacent plateaus. And secondly, that it is often on the current-facing side of the slopes, but not where waters have washed over the plateau. And this distribution then very much fits with the thinking that this is this wall of mouth that I have mentioned. So there is a driver towards larger eye sizes, so trying to get as deep and as close to where the prey first becomes available. And I think it also allows for alternative life history strategies, such as feeding on gelatinous prey, for example, to emerge. Because if you're standing in the currents and the food is transported to you, then you can reduce your own energy expenditure, and you may survive on low energetic prey. And this is actually what we are seeing in this species here. So when we're opening the stomachs or do DNA-based diet analysis, then we see that they're almost exclusively feeding on gelatinous prey. So far, we have only considered the mesopelagic species as prey organisms. But I also want to show that they can be predators and that they can control the life histories of some of the apex predators in the ocean, and in this case, bluefin tuna here. So I want to talk for a little while about a study that Daniel Ottman has been leading here, and what we have been trying to understand is how mesopelagic fish control the spawning behavior of bluefin tuna. So the assumption here again is that mesopelagic fish migrate and stay within the light comfort zone. So we expect lots of mesopelagic fish to be near the surface during the darkest moon phase here. So during new moon, we see lots of these mesopelagic species in surface waters, whereas during full moon, the mesopelagic zone, or the mesopelagic light intensities, more correctly, they are not found in surface water, so we don't expect them to venture near the surface. And several studies have hypothesized that it is therefore that lots of these species synchronize their spawning behavior with the moon phase. So what Danny has done, he has built a model that predicts the optimal spawning phenology for bluefin tuna. And as you can see, there's only a very narrow time window here where actually bluefin tuna larvae hatch from their eggs and are viable. And the onset of this is controlled by temperature. So early in the season, it is usually too cold for these eggs to hatch. But later in the season, it actually becomes too warm. So what you can see here, this little wiggle already is an indication of their, that both at nighttime they can't forage because it is too dark, but also their metabolism is really high, so they're burning up a lot of the energy. And towards later in the season, they are spending so much energy that they can't sustain this with encounter rates. So they're going into a metabolic meltdown. What we then have done is to add the lunar cycle on top and predation by some of these mesopelagic species. And what you can see is that we really see a drop in the fitness during the times when mesopelagic species are expected close to the surface. And I'm going to show this here for a second year, just to illustrate the fact that the moon phase is always slightly shifting between years, and it is never the same how the moon phase aligns with this window where tuna is actually spawning or is hatching from their eggs, which could also be a controlling factor for different year class strengths here. If we consider that in certain years when the spawning of tuna overlaps more with phases where we have more of the full moon period, then we would expect a stronger year class maybe. But what we are finding is that spawning around full moon for tuna increases the offspring fitness by 2 orders of magnitude roughly. So while this is a neat modeling result, we have also looked into the data to confirm these findings. And what we are looking at here is 2 decades of field observation of tuna spawning around the Balearic Islands. And what we are finding is exactly what the model predicted. So we are finding that tuna usually spawns around 3 days prior to a full moon phase here. It's really confirming what we predicted from the model. For the last 10 minutes of the talk, I would like to shift gears slightly. So far, I have talked about field observation and modeling, but I also want to talk a bit about how light and our own light footprint that we bring to sampling can bias our observations. This was very much the setting when I started on this project, so we were out in a little rip in the polar night in a fjord up in Svalbard at 78 degrees north. We were dangling a little echo sounder over the side of the vessel, trying to calibrate the echo sounder and find some jellyfish in the fjord. And we started talking about the effects of light on organisms in the water column, and we started wondering how much the 3 headlights that we had on would affect the distributions of organisms in the water column. So we decided to do a little ad hoc experiment. So we decided that we first only have the navigation lights on, then we turn all our lights off, all lights on, and then again slowly turning the lights on again, off again here. And what we observed then in the water column is that we really see a change here in the distribution of biomass. And that was for us somewhat concerning because we didn't expect that 3 little headlights would have such an effect already. And then we, of course, couldn't help but wonder what would happen if we actually consider the footprint of the mothership, in this case, the Helmer Hansen, which has a much bigger light footprint. So in the following years, we returned to Billefjord, a neighboring fjord also up there. We parked the vessel in sea ice, so put the entire ship in sea ice to keep it stationary. You can see that the sea ice is reaching right to the vessel here in this case. And then we did the same. We turned the lights of the vessels on and off periodically, and we observed what happens. And this is what we saw. And at first, this looks like diel vertical migration, but I can tell you the sun was below the horizon the entire time because we are in the polar night here. We had some moonlight, but also no major changes here. So what we observed is that we had instantaneous avoidance here down to over 100 meters depth. The fjord in this area is only 150 meters deep. We saw that the recovery was often slightly lagged, so it took about 30 minutes for the organisms to come back to the same depths that they had been before we turned the lights on. And there were also signs that maybe at certain frequencies, so we are looking here at 120 kilohertz, which is more a frequency where we would observe macrozooplankton, that we saw maybe some attraction in the periods where we turned the lights on, but obviously scared away maybe some of the predators here. And we repeated these experiments in several locations. Just going to show you another location here. This is in the neighboring fjord, very similar results. Again, organisms being scared away. We see this clear avoidance down to over 100 meters in this case. There were continuous avoidance in this case, so we see individual tracks that continuously avoid the vessel because the vessel was slightly drifting in this case. And maybe there is also some indication of accumulation here over time, which we cannot really explain so far. Again, a different fjord, same results, so I'm going to speed a bit through this. But we know these communities of these fjords very well, so the community is composed largely of some of individual larger cods, a lot of polar cod and some juvenile Atlantic herring, together with different species of krill and some northern shrimps. So this is the major part of the pelagic biomass here. What we did then is to move offshore into deep water, so we are over 1,000 meters depth here, and we again did our little light experiments, turned the lights on and off. There was very little biomass in the water, and we see little responses in the 18 and 38 kilohertz frequencies here, but we saw some large changes again in the frequency here for macrozooplankton, and again we see the vertical avoidance behaviors clearly. So it's not an effect that is restricted to the fjords. And we know in these cases what the community looks like. Again, largely some copepods, some krill species again, and some amphipods. So these changes are clearly observable. So we see changes in the behavior, in the distribution, but also possibly in the species compositions here. And then we wondered, is this a polar night phenomenon, or do we observe this also where we see a day-night cycle? So we repeated the experiments, this time on board of a Canadian icebreaker in the Canadian Arctic, high up here in Baffin Bay, but at a time of year where we had a clear day-night cycle. And again, you will see this clearly. We see these changes. Similar, different location, again, the same changes, and we see responses down to below 300 meters below the vessel. So down to mesopelagic depths, if you will. And we can see that while the upper layer is stationary here, we at least push down this lower secondary layer to great depths. So then the question becomes, if this is a sampling bias, how can we mediate that effect? So what we tried is then, or what we wondered is, will the organisms return over time as we keep the lights on? Will they get used to the new light environments? I'm going to show you two quick plots here, and the short answer is no. So we tried this on different occasions. These are rather short periods. We have also done one drift station with 24-hour lights on, 24 hours lights off, and we can clearly see the difference in the distribution even over a 24-hour time period here. So I would say that these responses are fast, they are persistent because we see no signs of acclimatization here, and they are consistent across season and regions. And then lastly, we wondered, okay, if it doesn't help to stay there for a long time, what if we go fast? So we tried the same again by steaming with 10 knots across the Barents Sea, which is a speed that you would usually use for acoustic surveys, for example, in the regions. And while we did not observe changes in all locations, there are several transects where we actually see also very clear patterns here with our lights on, lights off. Which makes the story even more complicated because we cannot exclude that it happens in some cases while we don't see the effect in other cases. So this is ongoing work, and we are still trying to unravel this story, but I think it shows that we need to be also conscious about light, not only in ecological interactions, but also in our own sampling. And it raises the question, what are we actually observing when we are taking samples at night? And with that, I would like to thank for your attention.
On point.
Thank you, Tom, for, I guess, amazing keynote for everyone. I hope there's a lot of questions, so please go ahead, and I will try to point, and if someone sees questions that I don't see, because I'm a bit blinded here, just give the microphones, and Tom will do the answering. I'm really blind. There's one here in the front, at least.
Thank you, Tom, Dorothy, Sintef Ocean Bergen. I learned so much, so I really thank you for that and for all the beautiful visuals. You feel like you're diving into the trenches of the North Atlantic. One thing that hits my brain is that advection, making the conveyor belt, connecting species, and are we, maybe Beth Scott is already doing this, but this idea of offshore wind and cumulative effects of offshore wind, because obviously offshore wind is designed to absorb energy that otherwise would be helping advection. And any modeling that we should be doing now to kind of predict this, to kind of perhaps give advice on where we don't want that energy to be absorbed.
I think for me it's very hard to quantify how much of that energy is absorbed there. But I know that colleagues are working on this, right? So there are people around the UK, but also other countries that have already started modeling this, yeah.
There's another one here in the front.
Hi, thanks. Really interesting talk. A long time ago, working on larval fish, I looked into scotopic and photopic vision and to what extent it made a difference for encounter rates in turbulent waters. I was wondering if you'd looked at that in terms of either interspecific or intraspecific developmental variation for some of the species in terms of the range of the habitat that's available to them in terms of light, because at the end of it, it's just waves at different lengths, right? And it's different accessibility potentially based on eye composition.
Yeah. Thank you for the question. I think this is probably my frustration as a modeler that I run into quite often, is that I notice here is something that I want to model and I don't find the data available. So often what we have to do is we have to borrow parameters from different species and try to get as close as possible. And I think these eye sensitivities is one of these cases. So for lots of these mesopelagic species, we would be super interested in doing all kinds of physiological experiments also on the eye. The problem is to keep them alive. And I think that would be one of the challenges for the future, is trying to get them into a laboratory where we can experiment on them and do some of these tests. But unfortunately, so I would very much welcome anybody who does experiments on eyes and light, because I think we are lacking a lot of the information there. Yeah.
Hello? Yeah. Hi, I'm Marta from MIPMA. I was wondering if using, for example, red light or just blue light, you would have a different response, because that can be a feasible, quick alternative kind of thing. Really nice talk.
Yeah, so that was, of course, our first thought as well. I didn't have time to show this, but what we have done is we created 2 underwater lights that we can program with different wavelengths and different light color spectra that we lowered on the CDD down and played what we call our fish disco. And we have tried a lot of different light intensities, different flickering rates, and we see avoidance across across the entire color spectrum, less so for red light, but still clear avoidance behavior, yeah. I think the paper is somewhere linked there in there. I dropped this in there as well. Yeah.
Hi, Leonie from the Antarctic Division in Australia. Brilliant talk, congratulations. That was really fascinating. My question is also related to the light avoidance. I was just intrigued how quickly this happens, and was wondering how they do it. Do you know how they sink so quickly, and how quickly they actually do it?
Yeah, so I think it looks maybe a bit exaggerated in these plots because it becomes very constrained. But I think the initial response is very abrupt, but that could just be also a change in orientation, right? As an organism maybe starts diving, we would see less area kind of that hits the acoustic beam, and therefore that echo would become smaller. I think I had a master student that looked at some of these rates, and then for fish it was swimming speeds of 20 centimeters per second, I think, down. So we are trying to look into these individual tracks and trying to see what actually individuals are doing and how fast they are going. But we haven't progressed to that stage yet. Yeah.
I had a question. You've been at sea in April, I think, and we were working with cameras in pelagic fishing nets during fisheries for the Greater Argentine.
Oh,
of
wonderful.
course, we were going to depth of about 600 to 800 meters, so you need a lot of light.
Yeah.
But then we had like 2 lights we worked with, both like giving like 5,000 lumens of power. And we really noticed that, like, we were wondering at what distance fish can see the light, because there was like significant less catch when my lights were on.
Yeah.
So of course they have like these huge eyes, but we're trying to find a way to do film but not lose fish in that sense. So we do have now several filters we will try out next year, but if they would want to escape the troll, it should be like a couple of 100 meters ahead where they already notice the lights, but I don't even know whether that's possible. I'm not really into the light stuff, but this was really interesting.
I wouldn't be surprised if they, at least strong directional light, if they could detect that at a greater distance, because the eyes are so light sensitive, right? I mean, you could see really how big these eyes of Argentine are. But yeah, I think it's a great challenge. Lots of these observations that we are doing, right, both with ROVs or landers where we have cameras deployed, we don't really have a solution to get around this, right? So when I joined colleagues of the British Antarctic Survey now down in the Southern Ocean, there was a team on board that tried to take actually pictures of the seafloor, but there the effect was the opposite. When the lights were turned on, so much krill started swarming around the camera, we couldn't take a picture of the seafloor below. So we had to turn it off, and then wait until the krill dispersed, and then turn it on quickly, take the picture, and hope that we were quicker than the krill. So I think you have both effects. Some species are avoiding, others might be attracted. Yeah.
Hi, Tom. Just listening to your talk, I think everyone here is a bit guilty of using different lighting to collect samples. Do you have any recommendations to correct these biases in most of the historical data that we collected and have been using with all these biases of light effects?
That's a very good question. I think this will be notoriously difficult because we have not measured the light footprint for all the vessels that we are doing this on. So we have started doing this and also trying to model the 3D light field around the research vessels that we are operating on. And there was one period where the light bulbs were changed. And that screwed up our results because we had to do the measurements again because it changed so much. So I think it will be very difficult to do this retrospectively for some of the observations that we have collected. Yeah.
It's time for one more question, maybe.
Hi, Tom.
Hi,
Really,
Johanna.
really great talk. So I wanted to go back to what you started on in the beginning, because it kind of strikes me as that this is probably something that fishermen have known for a very long time, you know, that the fishing banks are where it's like a high production, that's where the fish are. And I guess maybe it's, what I got from your talk is that this has kind of generally been explained as a bottom-up effect, so primary production, but you are showing that it's actually the opposite. Yeah.
So my thinking is that upwelled nutrients fuel phytoplankton blooms, and it usually takes some time for a food web to take hold, right? That phytoplankton needs to be eaten by zooplankton, that needs to be eaten by smaller planktivorous species until it reaches piscivores that we usually harvest. And I think the retention time across slopes, banks, seamounts is in many cases too short. So I think lots of the production would just be blown over these kind of foraging hotspots before it becomes available. So I think these foraging hotspots where we really see larger predators, I think they are fueled by advected prey organisms because they are instantaneously available to the predators that line these edges. And they come from great distances, and there is time for that food chain to kind of take effect. Yeah. So I think upwelling explains the large eastern boundary current upwelling systems and the fisheries production there, but I don't think it explains all the other hotspots that we're seeing around. Yeah.
Unfortunately, we are out of time for more questions, but please feel free to reach out to Tom or try to catch him before he has to leave today. Yeah, thank you again, Tom, for an amazing keynote. So please, a warm round of applause for Tom.
Thank you.
ICES Annual Science Conference is a thrilling setting that brings together the best scientists in the world, young and old, and in every discipline around marine science to talk about the challenges that we face today. It really is about each of us focusing on these big questions as well as our little pieces in the puzzle. And I think that this environment is the exact place to do this, and I couldn't be more thrilled looking forward about our partnership with the UK.
ICES as a scientific body represents a network of marine and fisheries scientists from around the world, so there could be no better place to be than the opening of their annual science conference here today. Quite simply, if you think about sustainability, there are pillars related to economic, environment and social, so we need to bring together all of those scientific disciplines to look at some of those big challenges that we face. We can't do that by looking at issues individually. We must look at all scientific disciplines together if we're going to have any chance of tackling some of those challenges that I mentioned.
Speaking to people at these kind of conferences can really help to inspire you and get you thinking about how your kind of career can shape itself in the future and give you new ideas about which areas to go into. So it's kind of like a long-term effect as well as kind of the short-term effect of helping with your work and meeting new people and meeting new collaborators.
I get to understand what's happening. It's one thing to look at it through research papers, it's another thing to discuss it with the people who are developing papers in the first place. Through the conference, I've made connections with really amazing people who have amazing ideas, and there's a lot of opportunities for collaboration.
The UK is committed to supporting and engaging and developing the next generation of marine scientists. We also aim to support and strengthen the ICES network, ensure ICES' future global success.
Incorporating social sciences, humanities and also people into the science of the seas is super important. I think we shouldn't forget that we're not managing fish, for example, but we're actually managing people. And how are they also impacted by the policy decisions that are being made?
It's very inspiring to see people who have worked their way out and then helping the world to become a better place.
Hi all, I am Marta Ferraro, and with Daniel Ottman, I am one of the incoming chairs of ICES. 6, we are the strategic initiative on the integration of early career scientists. And just the keynote that you just saw from Tom is just a perfect example of what we do for the integration of early career scientists within ICES. So, well, he did a great talk. It is a real honor for me to be here and close this year's, sorry, I'm a bit emotional. This is really an honor for me to be here and close this year's AAC. And for this reason, I would like to say that throughout the entire conference, I felt welcomed and fully engaged. And I know this will become an annual event for me going forward. You all know that this is a pretty big conference. In fact, 687 people joined this year. And however, these numbers doesn't really mean much to me, because for me, what is really important is that is this sense of community that I have experienced throughout the whole conference here. So obviously, as every year, there was groundbreaking research, and we were able to follow newest advances in the field. But what makes the ASC so special is how central science, scientists, and people are. And every year, you submit your proposals to SciComm for either a networking session or a team session. And so you have the opportunity to steer the direction of the conference and also to set the scientific objectives. And this is, something outstanding to me. And in fact, this, as an early career scientist, this is a bottom-up approach, which has been particularly empowering. And that's... So, for example, you may have participated to the ICES Showdown game, and our board game, well, the D&D-based networking session. And I feel like these are, complete new formats to conferences. But every single of you was very engaged, and I think that was a very nice way to look at science from a different perspective. But also, I think that the ASC brings focus on themes of equity, diversity, and inclusion. In fact, I think it was really revolutionary to see this session on creating supportive fieldwork environment in marine sciences. And as you see, I'm very enthusiastic about this conference and ICES and the people behind it. And I could go on for, at least 1 more hour. And I just want to point out that I think this enthusiasm is shared not only by me, but also by all the early career scientists, or many of them, because if you look at the numbers, more than 1/3 of the attendees in the conference are early career scientists this year. So, Alan, referring to your wise words from the opening ceremony, I think we can confirm that we are taking over here. But without further ado, I'm here to present the awards for some of the chairs that are outgoing the roles in ICES. So, our first service award is the Vice Chair of the Advisory Committee of ICES, Hen Oyave. Give it up to him. can move to the outgoing chair of the Ecosystem Processes and Dynamics Steering Group, Steven de Graer. So now we are thanking for the very hard work Debbie Pedreschi, chair of the Integrated Ecosystem Assessment Steering Group. Give it up for Debbie. Okay, and now we move to data. So we have the outgoing chair of Data Science and Technology Steering Group, Jens Rasmussen. And now, yeah, we're moving. We're moving to the chairs of SIX. Sorry. Yeah. And so I'm calling up on stage Alina Madita-Wieczorek, and Katel will take the gift for Amanda. Yeah, let's give it up for Alina. And yeah. And so now we're moving to the chair of the ICES ASC Strategic Initiative on Climate Change Impact on Marine Ecosystems, Alain Boudron. And now we are giving it up for the chair of the outgoing chair of Data Information Group, Shur Ringheim. Please. And now it's the time for the chair of the awards committee, Carl O'Brien. And yeah, now is the time for our outgoing chair of the scientific committee, Jörn Schmidt. He couldn't be here in person, but
dialing in from Penang, Malaysia. So good to see you, even though I can't see you. But very nice that the team made it possible for me to join you online. And thank you very much for that.
And now I'm leaving the floor to the Merit Award Committee, to representatives of them. And yeah, thank you very much.
All right, thank you, everybody. We are Evan Howell. I am the chair of the Merit Awards Group this year.
Hi, my name's Holly Perryman. This is my first time on the Merit Awards Group.
Yeah, so we had the privilege of being able to look at all of the poster presentations and the oral presentations this year. And as with every year, there were a lot of amazing awards or presentations to choose from. We did make a couple of changes this year. If you were at the last year annual science conference, it was a very vibrant and busy poster session. And when you're a judge and you have 25 posters to try to talk to people about, it was a little bit difficult. So this year we made the decision to go to a two-step process, and that was the reason why we asked for people to do their posters by the August 30th deadline. And so for this year, we did a pre-evaluation the week before the annual science conference, and so we did only consider the posters that were submitted by the time of the deadline. We'll do the same next year. We're planning to do it, so please do get your posters ready now because we'd like to see even more posters for consideration next year. And that's the magic cue. The other thing that I wanted to say is as we go through this, and Holly's going to present the posters and I'll present the oral awards, that for the oral and the posters, we were only able to consider work that was presented by the first author. So if there was work that was presented by somebody else that wasn't for consideration. So if your favorite talk was not up there, maybe that was the reason why. But again, we really appreciate everyone that went through the awards process with us. It was a joy. We had a great time. And with that, I'll turn it to you, Holly, for the posters.
Great, thank you very much. And it's so great to see everyone here. This is always a fun way to close out a great week. So first things first, we want to start by thanking. Yes, so first things first, on behalf of the MAC Group, I want to first thank the session conveners and all the poster evaluators. It was a lot of work and everyone did a great job. So can we just take a second to give everyone thanks? So like last year, this year, there was also a really great group of posters, and it was just, being my first experience this year, it was great to go through everyone's work. You're now looking at the top 5 of the evaluation process. And before I go through and award the 2 best posters, can we give a round of applause to these top 5? Okay, in no particular order, one of our top awards goes to Lorena Romano Martinez for the poster titled Investigating Fish Bycatch Uncertainties to Improve Antarctic Krill Fishery Management. They presented a library on the taxonomic and DNA information of Antarctic krill fishery bycatch, which was built through a thorough methodological process. This library is not only going to be a useful tool for the online observers, but also an important guide for fishers. It was a well-organized and informative poster, and the presentation was enthusiastic and enlightening. So, Lorena, please come up. So unfortunately, it looks like Lorena might have had to leave early, so we will make sure she gets her award. So the other award goes to Jenny Volstroff for the poster titled Review of Welfare Assessment in Wild-Caught Aquatic Species, a Fair Fish Database. They presented a way to quantify the welfare of individual wild-caught aquatic species and provided a database link where this information is being shared for many of them, offering an innovative and promising work on this issue in the fisheries context. The poster was clear and well organized, easy to understand for anyone, and the presentation was enthusiastic but also realistic. So please, Jenny, please come up. Okay, and thank you very much, and I'm going to hand it back to Evan.
All right, thank you again. So we'll go through the orals the same way that we just did the posters. And so first off, we would like to thank everybody that's on the Merit Award group. Please give a moment of applause for them. It is a lot of work. They had to put up with me, and I think that might even deserve more applause, but we'll talk about that later. Oh, great. Those that know me, yeah, wonderful. So again, we had a lot of great posters. We will go through the best presentation shortlist here. These were the top 5. Let's give them all a round of applause. And again, in no particular order, we award 2, and the first award goes to Patricia Porta for, there you go. So Patricia's title, as you can see, but the judges felt that Patricia's presentation addressed a topic that's seldom, if ever, done with fish data at a large scale. This covered the distributions and links between biodiversity, ecosystem function, and resilience of several fish communities in the Northwest Mediterranean. Patricia's presentation was clean, concise, and made a complex topic easy to understand. Okay, and again, in no particular order, second presentations for Carissa Gervasi from the UK. Let's give her. So if you're here, you can make your way up, but to talk about it, the judges felt that despite a complex topic with a novel approach, Carissa's presentation was easy to follow and resulted in an excellent, clear presentation with good visuals and without overly busy or text-filled slides to put the message forward. Her final summary slides solidifying the main conclusions for the listener. Enter stage left. All right. Okay, and so if there's anyone for the first presenter for the poster from the home institution that could come up, we can give the award to you and you can make sure it gets back to them. But with that, let's give a big round for all the winners today. And so with that, I'd like to ask ICES President Bill Karp to come up to the stage. Thank you.
Well, for those of you that were at the excellent banquet last night, don't worry, I'm not going to sing. But I am going to sing the praises of so many people, and in fact, everybody, because what makes an annual science conference is everybody. And if I had a list of the 672 participants, maybe that would be the right way to recognize that every one of you, whether you're a presenter of a paper, a poster, a convener, a participant in some other way, a volunteer, one of the organizers. However you play a role in this organization, you contribute, or in this annual science conference, you contribute to it in some way and to make this entire community, this entire network stronger. So for me, that's almost the greatest pleasure of participating in an annual science conference, is just seeing the community come together. But it's particularly heartening to see the way that the early career scientists are taking control, are really taking an increasingly larger role in every aspect, if you will, of the organization, and from the science and beyond. So Marta, you did an excellent job, and you just helped to illustrate that is exactly what's going on, and that is exactly what we want to have happen. Of course, I have some specific thanks to offer, and that's part of my job as I close the closing ceremony that Marta opened. I feel really fortunate to have grown up professionally within ICES. And as many of you know, my passion for fisheries and marine science was kindled when I spent 6 months at the Fisheries Lab in Lowestoft as a sandwich course student or intern before completing my undergraduate degree in the UK and moving to the US. So for me, it's especially poignant to be here with all of you in the UK in Gateshead as we reach the conclusion of another memorable ASC and, coincidentally, my term as president of ICES. As I mentioned, ICES belongs to all of us, and our science is diverse and innovative and is constantly invigorated through your creative and collaborative efforts. This is all showcased in ICES ASCs and is incredibly exciting, even to a very late career scientist like myself. As I said, I truly believe that each of you deserves credit for the various roles that you've played in this annual science conference, but I am going to recognize some individuals. The UK members of the ICES Council of Delegates, of course, the UK is the host. Each year we have a different country hosting, and the UK delegates lead the process of bringing forward a candidate member country and deserve special credit. Matt Gubbins and Carl O'Brien are the UK delegates, so thank you to them. Thank you to the organizations within the UK that have underwritten and provided so much in the way of resources to make sure that this has been another fantastic AFC. They are DEFRA, the UK Department for Environment, Food and Rural Affairs, and CFAS, the UK Centre for Environment, Fisheries and Aquaculture Science, and especially to the core local organising team, Tom Parker, Michelle Haggett, Beck Treeham, and Helen Eager. I'm going to pause now because I believe we have gifts for the delegates and for these 4 individuals who are the local organisers. And so if they're available, can we ask the 6 of you to come up and we can present you with these gifts. So where was I? Here, okay. I also want just a shout out for all the volunteers. They've made so much of a difference and made it so much easier for us to work through the details of the ASC. You see them in many different ways, but in particular, bringing microphones back and forth during the sessions and making it so much easier for us to have smooth interactions. So thank you to all the volunteers. And thank you also to the session conveners, as well as the paper and poster presenters. We saw the awards, but we want to recognize everybody who presented a paper and a poster. So thank you to all of you. And a very, very special thanks to the entire ICES Secretariat, led by General Secretary Alan Haney, and especially recognizing the work of Anna Davis, our ASC coordinator, but emphasizing the efforts of so many of the Secretariat throughout the year and during the conference itself. For me, working with all of you during the last few years has been a pleasure and an inspiration, and we are so fortunate to have you at the heart of our organization. As we adapt and respond to new challenges and opportunities, and as this ASC concludes, let's begin to make plans for next year's ASC, which will be hosted by Lithuania in Klaipėda, and let's start thinking about the exciting science that will be shared with this remarkable community in 2025. I think we have a video to show, but please stay, because as the video ends, we invite all of you to join us outside the meeting room here for a glass of champagne and some photographs, and to celebrate all of the achievements of this incredible week. So thank you very much.
You have to make something cooler than hot pink. Something truly unique. Cooler than hot pink.
I can't do it.
It's a traditional cold beetroot soup. Do you want some?
Good. Professor Gentiere, I believe we have the hot new color.
You mean cold?
Exactly.
Cold pink is in season. Wonder what else is?
Look, this is our country.
Come to Lithuania for colors you never knew existed. For more, visit www.lithuania.travel.